Okay, last time we were talking a bit about passband communication. And the basic idea in passband is that you have some frequency domain. So this is a plot of the Fourier transform of your signal. You have some bandwidth that's centered away from zero, in which you're allowed to transmit your signal. So there's some limited band B, there's a limited frequency space B centered around a carrier frequency FC. We argued that what you can do is you can take your baseband signal, multiply by this sinusoid, goes 2 pi MCT, and then basically what that does is it shifts it up the frequency domain like that. Okay, so now what we're going to do is we're going to look at, remember our hardware models for baseband. Basically, our hardware model looked like this. We had physical layer access, followed by the addition of some noise, followed by analog to digital. And this is sort of the line between analog and digital. And everything we care about in this course is to the right of this line. Then what we would have over here is our detection filter, HK, followed by some kind of decision device. And that would give us the bit 1 from 0. In passband, we do much the same thing. However, as I mentioned at the end of last class, so it actually makes a difference whether you choose cos or sine. And it turns out that cos and sine are orthogonal to each other, so you can actually use each of cos and sine to transmit a different signal. So the passband hardware model. So again, we have physical layer access and noise. That shouldn't change. And A to D. But then what I'm going to do is I'm going to do something called down conversion. Basically what down conversion does is it takes my signal, which is located up here in the frequency domain, center on FC, and shift it down the frequency domain so that it's down at baseband. Down conversion gives me 2 outputs, each of which carries a signal. This the in-phase leg of the detector, and this the quadrature. And basically what's going on here is that if I have a signal modulated with sine and a signal modulated with cos at the same time, this leg picks off the signal modulated by sine, and this leg picks up the signal modulated by cos, and they're orthogonal to each other, so they're independent. So I can pull off both signals. I can pull off both signals simultaneously without interfering with each other. So what does the down conversion look like? Basically what I do is I have my signal my two legs, what I'm going to do is I'm going to multiply up here by, so remember this is on the right of analog to digital, so this is now a digitally sampled cosine. Cos 2 pi FC KTS. This is a sine 2 pi FC KTS. So now what I'm doing is I'm expanding this box. I multiply by these cosines, and then what I do is I low pass filter. And that's basically what's going on in that box. We'll explore this in a little more detail in a second, but basically what this does is it shifts it down. It shifts it both up and down, and the low pass filter gets rid of the shifted up part. So all you're left with is basically the baseband signal that you sent with each modulation function.
Sir?
Yes.
So when in the down converter, first what's entering is in passband, right?
Yes.
And by multiplying it with cos and sine, we're sending it back to the baseband.
That's correct.
And then low pass filter gets rid of whatever is in the passband.
That's right. So we'll see that. We'll see this in a little detail right now. Okay, down conversion. So, what we're going to do, remember my modulated, my signal S of t, so I'm going to deal with continuous time for a second. My signal S of t is a baseband signal. And then what I'm going to do is I'm going to apply analog modulation to this, and I get S prime of t, which is equal to S of t, times a carrier, and that carrier is cos 2 pi FCT. So basically what I did, this has Fourier transform here in baseband that's centered around 0 with width of b. And this has Fourier transform width of b centered around FC. So this is stuff you should remember from signals and systems. So generally, it may be helpful at this point to remember that there is a negative frequency component. This is actually what it looks like in the frequency domain. Basically, I take this and I center it around FC and minus FC. That's really what's happening. So multiplication by a sinusoid means I take, so let's call the Fourier transform of this S of f. I center S of f around plus FC and around minus FC.